Hello and very good mornings. My name is Azmi Mohamed from UC Pendidikan Sultan Idris, Malaysia. The title of my presentations today is Surfactant with Aromatic Head Groups for Optimizing Properties of Graphene Natural Rubber Composite Surfactant with Aromatic Amine Polar Head. Have a look at the presentation outline. I'm going to start my talk with the research background, graphene polymer nanocomposites, graphene Phillips surfactants, followed by motivation of research, preliminary work, methodology, results, proposed mechanism, and last but not least, the conclusions. Alright, so since discoveries by Novoselov and Gims, graphene became one of the newest members in carbon-based families. And of course, graphene consists of one of atoms thin layer which build out from 6 neighbors of carbon arranged in hexagonal lattice. In general, we can say that graphene is one of mother of all graphite because possess outstanding mechanical, electronic, optical, thermal, and chemical properties. So why is graphene so powerful? Of course, because it's stretchable, harder than diamonds, thinnest material ever made, great conductor, and interestingly, it can be functionalized by, for instance, hydroxy or fluoride to form graphene oxide and fluorinated graphene. In Malaysia, graphene-based research is being covered by a National Graphene Action Plan where 5 main areas have been highlighted for application, including lithium-ion battery, conductive inks, plastic additive, nanofluid, and rubber additive. So as we know, Malaysia is third world large natural rubber production, and introductions of this interesting nanofiller can able to increase a large market size and its applicability. Quite a lot of prospects for natural rubber by introductions this kind of additive. One of the reason is a significant enhancement at relative small loading. However, the major challenge of towards this application is graphene itself is very hydrophobic. It's because limited dissipability in the polymer matrix. And this one of another reason is graphene also tend to self-associate, as result it produce aggregates and difficult to achieve optimal reinforcements. So therefore, numerous techniques have been introduced to prepare graphene polymer nanocomposite, for example, in the natural rubber latex, for example, solution mixings, mass blending, in situ polymerizations. However, this technique provides numerous advantages. For example, for the solution mixing, it requires volatile organic compounds through the process, and for mass blending, it provides a poor dispersion and failure start in the extruder. So one of the alternative way to produce graphene polymer nanocomposite is through the latex technology. Why this latex technology is provide a better technique is because the technique is a simple, applicable to most polymer solution. It can preserve graphene sp2 network and provide a uniform dispersion. In this technique, one of the main components will be introduced is by introducing of surfactant. We can help to able to stabilize the graphene in the polymer matrix. So as we know, surfactant of the abbreviations surface active agent. In the latex technology, graphene solution interface, the surfactants still are adsorbed driven by hydrophobic interaction, helping to separate the graphene sheets to prevent agglomeration through the electrostatic or steric stabilization. By using in the colloidal science concept, if the surfactant component have the favorable interactions with the water, we can call it hydrophilic groups. So same goes we use for the graphene, where if the surfactant component have the favorable interaction with the graphene, we also can use graphene Phillips surfactant or graphene compatible surfactant. So to date, numerous commercially available surfactants have been tested to disperse graphene. For example, ionic surfactant, SDS, SDBS, SC, CTAP, and NDI. Meanwhile, Meanwhile, for diionic surfactant, several surfactants have been tested, including Triton, Pluronic, Twin Series, Tetronic, and C12E5. For the ionic surfactant, among all, SDBS become one of the most efficient one because it's able to exfoliate and disperse graphene up to 7 days with a cheaper cost. Meanwhile, ionic surfactant Twin 20 become one of the best surfactant to exfoliate through TIPS ultrasonication, which is disability up to 7 days with the cost of 7 cents per gram. So for further information on regarding of surfactant performance, you can have a look at our publication in Advanced in Colloid and Interface. So despite numerous surfactants have been tested, majority of the surfactant is focusing on the commercially available ones, and up to now there are no systematic study been done on surfactant design for designing or stabilizing graphenes. So therefore, one of the multiple way to is through the modification surfactant chemical structures of AOT or aerosol OT. So AOT or aerosol OT, or the full name is dioctysodium succinate, is the typical food active emulsifier, disperser, and wetting agent, and can be easily prepared through 3 main steps with a higher yield up to 85%. And this is also part of parcel experience in our group to prepare the surfactant to stabilize water in CO2 microemulsion, which is been published in the following papers. So before we proceed the experiment for the graphene in natural rubber latex, we did some preliminary study using carbon nanotubes where two different surfactants were synthesized, which is by introducing a phenylsburyl group in the surfactant chain of TC2PH2 and TC3PH3, and this synthesized surfactant were cross-compared with the commercially available SDBS. Interestingly, by introductions of phenylsburyl group in surfactant chain, able to stabilize the carbon nanotubes in the natural rubber latex. And we believe that the increasing of the phenylsburyl group increase the pi-pi interactions between the surfactant chain and carbon nanotube and helps or stabilize the carbon nanotube in natural rubber latex structures. And in this project, we did the similar concept where TC3PH3 we again cross compare with the commercially available of SDS and SBDS, and in this project, in order to increase number of phenyls group, we counter ion exchange of the sodium ion of the surfactant with the anilines group to become anilinium's counter ion as DSAN, DBSAN, and TC3PH3AN. And all the surfactants were used to prepare the nanocomposite through the latex technology, which is summarized in the following figures, where at the first stage surfactant solution we mix with in this project we use graphene nanoplatelets through the stirring and sonication to produce surfactant stabilized GMP dispersion. Meanwhile, the surfactants stabilized GMP dispersion were added with the polymer to produce through the sonication and drying to produce nanocomposite. And for the nanocomposite, 4 different techniques were used to characterize the composite, including 4-point probe to measure the conductivity, Raman spectroscopy, FESEM, and HRTEM. Meanwhile, for GMP surfactant dispersion, we use zeta potentials as well as small angle neutron scattering. So for the first result is a 4-point probe result, which is electrical conductivity. As you can see, the introductions or the increasing of the numbers of phenyls groups not only on the surfactant chain improve significantly the conductivity of the composite up to -2, and this is our FESEM image as HR10. In order to study the defect of the composite by introduction of surfactant, we did a Raman spectroscopy, and this is be indicated through the intensity of by calculating of the intensity of defect band at 1350 and a graphitic band at 1582 ratio, which is we call it SID-IG ratio. And as you see, all the composite provide the similar ID-IG ratio, indicating that the GMP, the SP2 network of the GMP in the composite remain intact. Okay, the next one is in order to study the stability of the surfactant solution that we added through the latex technology, we measure the zeta potential, where as we see the zeta potential value more than 30 MV indicate that the surfactant solution is stable. And as you see, all the surfactants are stable. However, among all, the TC3PH3AN shows the highest stability in comparison to the commercially available of SDBS and STS. And this is consistent with the magnitude of enhancement of electrical conductivity of the composite. So for last characterization, in order to study the shape and size of the micelles, we did a small neutron scattering measurement. This is carried out at the LIQ instrument in Rutherford Appleton Laboratory under supervision Dr. Stephen King. All the data were fitted in the following tables. And as we can see in the following table, the characteristic of self-assembly of the surfactant can easily control by changes of surfactant molecular structures. And as you see in the table, swapping the sodium counter ion aniline groups in the counter ion change the globular structures of SDS, SDBS, and TC3PH3 to the rod-like or bilayer transitions. And it's believed that the introductions of phenol groups in the surfactant chain and the head group increase the pi-pi interactions with the graphene sheet. And the next one is a scattering nature of the GMP dispersion stabilized by the surfactant. And as you see in the table, the presence of GNP does not encourage the structure transition, especially for the SDS, SDBS, and TC3PH3. However, for adenine groups, except for DSAN, the surfactants undergo shape transition into multi-lamellar shape, where GNP dispersion could be detected by increment of the bilayer counts. For conclusion, observation of surfactant structure and composite properties have shown the modifying of surfactant chemical structure have profound effect on electrical conductivity enhancement and surfactant aggregation behavior. And the presence of anilines in the surfactant head group improve the interaction between surfactant and graphene surface. That is by bringing the surfactant molecule closer the graphene surface for enhanced pi-pi. Before I end my presentation, I would like to thanks to my university for the sponsorship, Masanobu Sagisaga team in Hirosaki, Julian Isto in Bristol, and Stephen King in Rutherford Appleton Laboratory. Thank you.